You have to click. Got it. And
Yeah, so the floor is yours.
Okay, and the screen sharing is working via Zoom? Yeah. Yep, okay. Okay, so good morning, everyone. I wanted to thank Jenny again for organizing this. It's so nice to be talking to people in person. So what I wanted to talk about was I've been sort of watching the development of large language models over the last few years and looking at what they're accomplishing. And it's pretty amazing in terms of what they're accomplishing and able to do in terms of reasoning, but also missing something. And what I wanted to do was talk about talk about compositionality. And this is a difficult question, a little tricky to define, and so I won't spend too much time on that aspect. So I'll try and give lots of examples. So I think it's one of these things that's easier to understand by example than definition. And when I'm talking about large language models, just what I'm talking about is transformer networks and the systems that have been built using them, like so GPT-2, GPT-3 are the underlying large language models, and then systems built using them are things like ChatGPT and Palm. And a couple of examples of what these kind of models can do. When they first started coming out, they were quite amazing in terms of what they could do. So here's an example that Gary Marcus gave. Description. It's a toy problem. John pulled. This was a prompt. Exactly this prompt given to ChatGPT. John pulled out of a bag a blue vase, a red apple, a yellow banana, a black pen, a red rose, and a green cucumber. What was the second red item he pulled out? And ChatGPT 3.5, and I tested this on March 24th, replied confidently, the second red item John pulled out was a red apple. First time I read that, I thought, hey, wow, that's amazing. I got the right answer. But if you look more carefully, that was the second item. It wasn't the second red item. But ChatGPT 4 manages to fix a lot of these problems, and it correctly replies. ChatGPT 4 was also trained to give more concise answers, and it just replies a red rose, which is correct. There's these models are advancing at quite a remarkable rate. Try and put
that. You can click on over there.
It's okay. I don't think I have anything on that area of the screen. So I want to spend a couple of slides on background here. Like I said, I wanted to talk about compositionality, and I'm going to talk about it in a pretty broad sense of thinking about, that involves things like variable binding, which seem essential to compositionality. And the type of things that people do and that we'd like to program AI systems to do of reasoning, language understanding, generalization when learning, all of these seem to involve combining concepts in a compositional way. And in the late 80s, Fodor and Polishin had published a very influential critique of neural networks and connectionist systems that claimed that connectionist systems lacked a mechanism for combining concepts in compositional way and doing things like variable binding. And this motivated these observations. Fodor and Polishin's critique, it wasn't like a revelation. These things were obvious to a lot of people. They just expressed it very well. And these concerns motivated a lot of work in the area. Particularly my work was looking at how could we do these kind of compositional operations in neural network type representations. So, just and then jumping forward, there was a online workshop last year in June last year that addressed this topic of compositionality in AI, and this was a lot of interesting things. This was a 2-day workshop. If people haven't seen it, I highly recommend looking at the presentations there. A lot of very interesting stuff. People went into a lot of length, to try and define what compositionality is, and to look at how you could test for compositionality. Some of the really big questions coming out of this workshop, and at least from my reading and listening, two of the big questions were, does AI need to have primitive binding and composition operators? And that is what I see. That's one of the central things that VSA provides, is primitive operators to do compositional things like variable binding and hierarchical construction of hierarchical representations. So that was one of the questions. Another, and there's some real, I think it's a genuine question whether you actually need those primitives. My inclination is that yes, you do, but I think it's totally open for a debate whether you do or not. Another question was that to solve compositional problems, to do complex reasoning problems that appear to require sort of manipulation of compositional representations, does that need some explicit representation of compositional structure? And the general sense that I had of listening to all the presentations at this workshop was, for the first question, does AI need primitive binding and composition operators? Totally spread out spectrum of opinion. So some people saying, no, we don't need them, that these things can just arise out of other mechanisms. The second one, does solving compositional problem require explicit representation of compositional structure? There, the answer is more on the yes side, more of a consensus of yes. And I'll show some types of problems that sort of get to that question. The interesting thing about large language models is that they appear to exhibit compositional behavior and able to solve compositional problems without having either of these things. They don't have any primitive binding operations, and they don't really have any explicit representation of compositional structure. And so, I'll try and dig a little bit into more of those. So, want to very briefly. There was a lot of time spent on sort of trying to define what does compositionality mean, and I'll put up a definition here. Like half of the presentation spent a lot of time doing this, trying to define this definition here. And this was one that Gary Marcus used, and wherever you see this, try to give make it easy to look for the references. COC is the Challenge of Compositionality conference. So Gary Marcus there, his definition that he took from Szabo in a 2008 publication called The Case for Compositionality. The definition, the meaning of a complex expression is a function of the meaning of its constituents and the ways they are combined. This type of, it seems reasonably straightforward. This type of definition was actually pretty controversial because it's necessary but not sufficient. And so people had other definitions, but I won't go into those. There's lots of one of the interesting things about this area is the range of types of problems that involve compositional reasoning. And so these can go all the way from very synthetic problems that you could easily construct very large data sets, like arithmetic problems expressed as a formula. So just the string 2 space plus symbol space 2 equals 4. And it's easy to construct lots of examples like that and then test how well a system performs. And can go all the way to various kinds of natural language problems. And so, making inferences of like puzzle type problems expressed in natural language, math problems expressed in more natural language. One of the interesting things is that it's when you get to problems expressed in natural language is that it's actually surprisingly hard to tell whether systems that do well on the benchmarks, are they actually doing any sort of compositional reasoning? And the reason is that when you're dealing with natural language, very simple kind of heuristics go a long way to solving many problems and can produce an illusion of the ability to do compositional type of processing. Okay, so I'll try and give a few more examples of types of problems. So Ettinger at this talk, one of the comments she made that the compositionality, that's the way that we avoid having to do infinite memorization, right? Because it can just productive. You just learn a few rules and you can do an infinite number of tasks. She talked about the various kinds of compositionality. There's syntactic aspects of compositionality. So think just binding the components of a sentence to the role that they're filling in the sentence. So the difference between the waitress served the customer and the customer served the waitress. The other example that she has here, this one's a bit more difficult to understand, but it gets at something that's sort of important when you're combining concepts and phrases. It's the ability to pick out what's important and what matters. So here we've got an image of an older woman smiling with her fist up in the air, and an image of a kitten labeled cat. And then how do we combine this to old cat? And we have a smiling kitten with its fist up in the air. We picked up the wrong semantic angles there. Here's an example of the type of problems that she was testing on, which shows how these simple heuristics can give an illusion of compositional behavior and performing well on these tasks. So here's a simple problem. And version 1 is vulnerable to heuristics. And the problem is Sebastian lives in France. The capital of Sebastian's country is blank, and the system has to fill in the blank. And it can, these systems can do things like this pretty well, but can also do these well using simple heuristics and basically type conformance heuristics. We're looking for a capital, there's a recently mentioned country, what is it? And that was the same kind of answer that we saw in that first example where I gave, where it just sort of picked out the first thing that sort of matched. And the way that you can control that you need to look at these systems to test whether they're actually understanding the structure is you need to understand what those heuristics could be and solve and control for them. So this kind of heuristics you can control for by you create examples where the heuristics fail. So distractors. So here, distractor, Sebastian lives in France, Rowan lives in Indonesia, and Daniel lives in Chile. The capital of Sebastian's country is, it's the same final sentence before, but now we've got distractors. And this way you can get a lot more insight into the actual abilities of these systems. Another example of kinds of compositional problems people looked at, Linzen had talked about a lot of work they did in trying to understand whether these systems can understand the compositional structure of language. And one of these examples he talked about was just having sentences expressed in different ways. And the job of the system is to convert the sentences to some canonicalized, normalized form. And then you could see that they're the same. So all of these sentences would mean the same thing. Can a system identify that? And Linzen talked about two types of compositional generalization. And the distinction here is sort of interesting because the two types, lexical generalization is a simpler kind of generalization where you're seeing the same, and here we're specifically talking about linguistic structures. So the same linguistic structures that we've seen before, simple subject, verb, object sentences, but you're seeing the filler in a position that you've never seen it before. And can systems generalize? And generally, the opinion was that this type of generalization is a simpler kind of generalization, and this is just a role filler type of compositionality that you need. The other kind of generalization is structural generalization, where you have nested structure. And so here we've got one, in your training set, you might have something like Ava saw the ball in the bottle on the table. And then what you want to see is, can a system generalize to structure a more deep structure that it's never seen before? So now Ava saw the ball in the bottle, on the table, on the floor. We've got one more level of nesting there. And the general sentiment at this, from all of the presenters, this is the kind of generalization that the current language models have real problems with. And it's also really difficult to test for. And so here's some, I won't spend too long on this. This is results from various kinds of systems on looking at their performance on these two types of generalization. And this is the lexical generalization, and there's a bunch of different systems there, and they all do pretty well on lexical generalization. For the structural generalization, only the models that were, these ones down here, that were specifically constructed to and had additional mechanisms on top of the large language models, only those kinds were successful in doing these kinds of structural generalization. So what I want to do now is transition more into talking about the large language models and how they, how do they relate to compositional operations? So, the claims at this conference, Gary Marcus, who's been raised a lot of really interesting criticisms of the capabilities of large language models. His claim was that large language models don't implement compositionality. Basically, they don't implement it at all, and this is a huge problem. That's his position. And it is a general, it's been commonly observed that merely pre-trained large language models, so the models that are just trained on the word prediction, that haven't had the additional training of systems like ChatGPT, those kind of models are just incredibly weak at compositional, things that a calculator can do easily. We have a supercomputer simulating these giant neural networks, and they can't add 47 and 82. It's sort of amazing. And in general, the people looked a lot into various tests of systematic reasoning and finding that these models, despite their amazing ability to produce very fluent and intelligible output and solve lots of problems, that they really do struggle a lot on tests of systematicity. And this seems to be a very dynamic area. So Millier, another participant at this conference, did a lot of experiments with trying to build systems that would do more compositional reasoning. And his conclusion was that the initial results were pretty poor of what they could get out, but they found that small tweaks could make big differences, and that the devil's in the details, and they found by doing lots of small tweaks they could get surprisingly strong performance out of the system. There's a lot of interesting stuff there about how apparent, some types of behavior that look like they're solving compositional problems, that they're being solved through non-compositional heuristics that perform very well. There was, this perfect title on this paper, Right for the Wrong Reasons, Diagnosing Syntactic Heuristics in Natural Language Inference. And that was from 2019. Ali Pavlik and Tel Linzen were presenters at this conference. One of the very recent developments with large language models that's improved their performance just astonishingly amount is the chain of thought prompting, where models are shown sort of basically the idea is show your work, like when you're learning in school, show your work and the teacher can grade you, and showing your work helps you reason through a problem and carefully follow the steps. And that seems to work amazingly well with these large language models in solving problems. And interestingly, people have sort of asked the question, how can these models do so well with chain of thought reasoning? And one of the major hypothesis that I've seen is that the training data that has enabled chain of thought reasoning in large language models to work is the code that it was trained on. So computer code, because computer code is sort of very sequential, and reasoning about what computer code comes next, that's the kind of thing where you need to do this reasoning that from what has come before to stepwise to what comes next. Here's an example of chain of thought prompting. So this is at the top, look on the left over here, this would be the input to the model. So you're showing exactly this text. Question, Roger has 5 tennis balls. He buys 2 more cans of tennis balls. Each can has 3 tennis balls. How many tennis balls does he have now? The answer, and this is all the prompt that is shown to the model. The answer is 11. And that's showing an example of what the system should perform. And then the question is, the next question that the system is meant to give an answer to, cafeteria had 23 apples. If they used 20 to make lunch and bought 6 more, how many do they have? And the model gives the answer is 27. It's wrong. It's sort of, well, it gave a number, that's good, but it was the wrong number. But what chain of thought prompting does, it says, okay, model, I don't want you just to give me an answer. I want you to explain how you got at the answer. And so the difference now is in the answer to the first one, it's showing what you should do is explain each step. And just breaking it down into these individual steps, now the model output is an explanation of the scenario and step by step, and it can give the correct answer at the end. It gives the correct answer that it's 9. And this just works phenomenally well. And here's some examples of the types of performance increase that people see with chain of thought prompting. So let's see, these ones with, this was This was GPT-3 without chain of thought prompting, and then with chain of thought prompting, going from 33% on the problem solving rate up to 55%. Then this was a Palm model. This is a model that Google has published without chain of thought prompting, just the standard prompting, 18%, and then with chain of thought prompting going up to 57%. They're impressive gains, but also, what I find a little bit unsatisfying is there's still a lot of headroom here. These problems are not that difficult. Why, we should be getting closer to 100%. A lot of these problems that are in these large benchmarks, they don't always have clear answers. So you don't think of it that we could always get 100%. But these were these math word problems, and yeah, I think we should be getting 100% on that. So one of the questions that comes up is whether, well, does this chain of thought prompting allow large language models to be compositional? And what some people see as happening is that these transformers, these very large models of these attention heads, and the attention heads allow dynamically deciding which inputs to combine together. And to some extent, these can keep track of compositional structure, but I think it's a real question to what degree they can do that. But they definitely seem to be able to do that as a little bit. What Smolensky was commenting that the transformer networks, if you think about it, they do allow a kind of variable binding, because you could have one column in your transformer can be its attention mechanism can pay attention to to some other value, either an input or some processed embedding higher in the network, and that is a type of variable binding. Not that versatile though, but perhaps you could go a long way with that. So looking a little bit more in depth at transformer networks, they're this very regular structure where each input token has a column of network above it, and at each layer of that network, you have this crossbar attention mechanism that can pay attention to the preceding layer in any other column, and this is very versatile. And we have these. So in the orange here, these are the activations at each level. They're like a hidden layer, so it's like a vector at each level, and these are propagated upwards. The orange, so that the activations are in orange, and they go through these mechanisms. The attention mechanism in blue, which has matrices which transform these into other vectors, for the attention mechanism, which calculates a dot products and then does a weighted sum, and then it goes through a feed forward network to arrive at the output of a layer. And each layer is like that, attention followed by a feed forward network. The feed forward layers are a matrix multiplication of the activation layers, and you could view that, hey, could that do a type of binding? Because a matrix times a vector operation, you can implement binding like that. But the matrices that are multiplying the activations, they're learned, but they're not dynamic. They don't depend upon the other inputs. So it's not like we're able to bind together information. We can't take, like, if this was a description of a role and this is a description of filler and combine that dynamically. It's not able to do that. But with what it can do, it can accomplish a remarkable amount. So, could these large language models be representing compositional structure without actually having any primitive operation for encoding encoding this compositional information like variable binding, and even the hierarchical compositional structure. So maybe one way they could do it is by, well, we do it all the time in natural language. We encode compositional information in text, in just strings, and that's what these models are great at outputting, strings. So here's an example. This one with structural generalization. Expressing this problem is just expressing all of the relationships in this sentence, all of these relations in a logical form, but each of this is just text, and these transformer networks can output that kind of text. So can they accomplish that kind of compositional reasoning just using those mechanisms is a question. What this was from. These examples were from this paper by Weisenhorn, and the claim of the paper is in the title: compositional generalization requires compositional causes. So what they were demonstrating was that on these types of problems, transformers could not achieve top level performance, and to achieve that performance did require building more explicit compositional mechanisms in there. One of the, I think Ross was mentioning to me yesterday, there was another example of this recently, but this, could we build, these kind of compositional operations directly into transformer networks and give them the capabilities to more powerfully reason in a compositional manner. And Smolensky did this together with Schlag and some other colleagues in 2019, where they introduced some tensor product operations. It was basically element-wise, doing binding by element-wise operation. So what he did was just add, and normally the attention mechanism involves three vectors: a query vector, a value vector, and the key vector. They added an additional one that was a role vector and put that into the network. And so this gives what I was talking about before was missing. It adds a composition primitive to the transformer system. And what they showed in that 2019 paper, they were testing it on these kinds of math problems. And this is exactly the text that is input into the model, and then the model is meant to give an answer. So the question is, what is the first derivative of, and then you've got an expression, and you're meant to produce the answer to it. Or calculate 66.6 times 12.14, and the output is meant to be 808.524. And what the results here was that they did get an improvement from their system, but I was a little bit surprised at how small the improvement was. Adding their implementation of a transformer got 53% correct on their data set, and when they added the tensor product operation, they got up to 54 or 55%. Surely we could do better than that. I mean, I think it's fascinating that it works at all. They had a simpler task in the 2022 paper, and this one's very easy to understand. The task they had was just a copy task. So given an input of open parentheses 3, 9, 7, 4, 7, close parentheses, you had to output exactly the same thing. And the ordinary transformer networks have trouble with this. And what they showed was that their model could quickly get to very good performance, 100% performance, but not always. And they tested 3 types of models. The red one was a LTSM network. The green one was a regular transformer network, and then the blue one learned very quickly and got up to 100% in a lot of cases, and that was their transformer augmented with the tensor product operation. So, I think that's one really interesting direction to go. Want to return to some interesting examples of are these existing systems like ChatGPT seem to be doing something like variable binding. And so here's an example. This is a problem I just input into it last night. And this is like a shell game reasoning. And this seems, I constructed this one, seems to be something that you need to do something like variable binding for. The problem is Alice has a green ball, Bob has a red ball. Alice gives her ball to Kathy, Bob gives his ball to Dave, Kathy gives her ball to Bob, Dave gives his ball to Alice. What color is the ball Bob is holding? And ChatGPT 3.5 has a brilliant approach to it. There's let's trace the ball transfer step by step. And it does it. And it traces down, at the 5th step, Kathy gives her ball to Bob. Now Kathy doesn't have a ball and Bob had, and gives the answer. Therefore, the ball Bob is holding is red. And I saw that and I thought, okay, that's pretty remarkable. And then I had one beer, so I have to read this a couple more times. And circled in red, at step 5, it concluded, and Bob has the green ball. And then step 6 was Dave gives his ball to Alice. Now Dave doesn't have a ball and Alice has a red ball, and then gives the answer. Therefore, the ball Bob is holding is red. But it had correctly reasoned at step 5 that Bob had the green ball. But this was a heuristic that it looked like it was picking the last thing. ChatGPT 4, which had a remarkable increase in reasoning power, does the same reasoning in a more concise way and gets the correct conclusion. It's that the Bob is holding the green ball. And and to me that looks a lot like variable binding. So I want to end up with some observations of what's going on here. This chain of thought reasoning, it led to this remarkable leap in performance. But it seems like there's still headroom on compositional reasoning tasks. That ChatGPT 4 narrowed this headroom a lot. What is missing here? And one obvious thing that you could say is missing is compositional primitives are missing. But do we really need them? These systems seem to be doing a remarkably good job without having compositional primitives. Maybe we don't need them at all. And this is what there was real divergence of opinion on at this conference. I think this is a totally open question at the moment. So maybe we don't need compositional primitives. Maybe we just need the right ways to structure these problems. And thinking about how the chain of thought reasoning seems to be going, very, very interesting direction. And if you think about how people learn, we don't just give them textual descriptions of complex tasks and expect them to regurgitate the right answer. Showing your work is a time-tested way of that students learn, and that people, pilots have checklists, and doctors in hospitals have checklists for operations. We have also flow charts. All of these things are aids to performing reasoning. So one thing I want to mention here, there's been a lot of hype around the large language models and some claims of emergence, that these abilities that they don't appear in smaller models, and then all of a sudden these abilities appear, and this is kind of some sort of creation, remarkable creation mechanism. I think these should be taken with a large grain of salt. There's a really interesting paper that just came out this year. Another great title, Are Emergent Abilities of Large Language Models a Mirage? And they largely answer yes. They say these are the claims of emergence where you suddenly see these abilities or these remarkable abilities appearing in large models, that all of a sudden it happens, that this is more of a function of the metric than of the capability. And that because the metrics basically measure an all or nothing thing. So, but if you have a different metric that looks more at the components of what goes in, then it's not emergent, it's gradually appearing. This is a very interesting and convincing paper. And I think getting on my last slide. Yeah. So, what I see as the open questions here are, the first major open question is, do we need a primitive operation for compositionality and variable binding? Existing large language models seem to perform remarkably well without any explicit primitives like that. That you can view the positional encoding and the attention mechanisms. Those could be adequate to perform some simple kinds of variable binding, because they can have associations between different places in the network. But if we added compositional primitives to these networks, like Smolinski did in that one example, what could we get? I think what Smolinski showed you could get far better generalization from fewer examples. These models require immense amounts of data to train. And the other thing that I think we get is, this is what we were talking about last night, was that we could get much greater transparency into what these systems are actually doing and why they're producing certain answers. The other open question was, what kinds of real world tasks and benchmark tasks can we have that require compositional reasoning? And there, what's important to know is what kind of performance can you achieve on those tasks without actually having true compositional operation, because the ability to use heuristics. And then also, what are good tasks for training and testing reasoning machines? And there, I think there's still a lot of potential for developing new kinds of tasks. There's only been a few kinds of very simple tasks, like the mathematics problems, where you can generate large amounts of data. I think potentially, one of the things that these networks don't seem to have the ability to do is chunking. So sort of recognizing something, here's a larger structure, how can I build a compact representation of that and then manipulate that as a chunk? And so that might be an interesting direction to go, is to try and create artificial tasks that involve chunking, and then use that to probe the capabilities of these networks. Okay, so that's everything I wanted to say for the moment.
Thank you, Tony. I suggest we start with a question in the chat from Joshua. So can you read it loud? Because small letters.
Joshua, would you like me to read out this question?
Oh, no, I can read it out if you like.
1, 2, 3. Okay, Joshua's question is there an argument to be made that compositional reasoning is an all or nothing ability, in the sense that if it is truly the thing that's happening, it should happen all of the time or none of the time? So I think my response to that would be that there's lots of different examples of compositional reasoning. And I think one of the earlier slides that I showed identified two kinds, what they called the lexical generalization and structural generalization. And the lexical generalization has to do with variable binding, and the structural generalization with manipulating hierarchical structures. That's one way in which you might be able to do a decent job on one, but not the other. There's also the question of heuristics. that I suspect that with natural language, it's something that, people, when they're solving problems and interacting with the world and interacting with other people, that how they do it, a lot of it might be, a lot of it is heuristics. How much of it is heuristics, how much of it is sort of what we might think of as syntactic language processing. I think it probably varies a lot between people. So I, combine to some extent, it could be an all or nothing thing, but that's, once you have it, then that's sort of the kind of thing where I was saying we should be able to, these problems that have well-defined answers, we should be able to get 100% on them. So in that sense, yes. In the sense that, well, a lot of these things we can do with heuristics. In that sense, no. Yeah.
Yeah. Could you indulge me with a 5-minute comment?
I mean, that's why we're here.
Okay. Tony, if we can go back to about, I don't know, slide 2 or so. I think it is ultimately relevant to what you just said, but it takes a bit of setup to get there. Next one. Yeah, that one. Oh, no, next one. Sorry, next one. Oh, no, there. No, it's back to the previous one. It was the, does AI need primitive binding? If you move to, can you move?
Yeah, that's what I'm trying to.
Okay. We'll get to the final point, but I think from a VSA point of view, and I think there is actually a VSA view on this, which kind of makes these questions, I have difficulty saying, do they mean anything as questions? So this, does AI need primitive binding and composition operators? Do we require explicit representations? To me, comes from an assumption of a classic good old-fashioned AI, I'm writing a Lisp program or I'm doing formal logic kind of a position. And the thing about formal logic is it's all about form. It's basically, I have a set of tokens and all I'm doing is shuffling them around according to a set of rules. They don't bear any relationship to anything outside. But all the behavior of the system comes entirely out of what's there in these tokens, which are inherently meaningless, and the rules which constrain how you can shuffle them around. I'm more a duck theory kind of a person, and I think this is, as in, if it looks like a duck and it quacks like a duck, then it's a duck. And I think that with VSA, there's this representation function duality kind of a thing going on. If you've got a binding, it's just a vector, it's like any other vector, but it also expresses a transformation, and that transformation can be applied. So I'm more concerned with the functionality of the system. So if it's functionally performing in a way which is consistent with whatever you think compositionality is, then I don't see whether it looks like it's got bits in there which are compositional or not is relevant. I'm concerned with, does it functionally perform in a way which is like that? And I think that sort of particularly becomes an issue in VSA because everything is simultaneously data and functions. So that's sort of the backgroundy bit. Then the syntax, so once again, formal systems and syntactic stuff. So the cat sat on the map. Right. That's a nice little sentence we can parse it, and putting aside it's actually linguistic, and I think linguistic examples are typically very misleading. But anyway, there's that, the cat sat on the map. From the syntax point of view, which is your rules for formally shuffling it, your grammar probably says something like, oh, I'm treating that as though it's a determiner, a noun, a transitive verb, a determiner and another noun, which means that syntactically it's equally valid to say the mat sat on the cat. That's syntactically, and that's compositional. You've got the rules are allowing you to compose those components in different ways. But it's the kind of answer which would be a compositional answer coming from ChatGPT or whatever, but people would look at that and say, well, ChatGPT doesn't know what it's doing. Now you can get around that to some extent. So essentially what classic AI has tried to do is to set up grammars which captures some of the meaning of the external world. So instead of saying, I've got a determiner and a noun and so on, you'd probably say, well, there's all these different categories of nouns which are syntactically different. And I've got a category of noun which is, pet nouns. And I've got a category of noun which is floor covering nouns. And in that kind of a grammar, you're probably not going to get the mat sat on the cat. But there's an old slogan in linguistics: all grammars leak. That a grammar will generate some sentences which are not grammatical, and there are some sentences which exist in the world which are valid, but not grammatical according to the grammar. But essentially, what I think from your clear presentation is I'm quite happy now to believe that what things like ChatGPT are doing is actually compositional. What it's lacking is meaning. And that by exposing it to 10,000 human lifetimes of text, it's effectively creating a grammar which it's applying compositionally, which is capturing a lot of the regularities of the world, but not all of them. And so I think that the issue is actually not compositionality, but how would you set up a system to capture external meaning rather than being pure internal symbol shuffling?
Yeah.
Okay, end of rant.
The grounding. Yeah.
Yeah, so to add on to that, so a few things here. Thing number one, there's the paper, popular networks is all you need, which seems to imply that transformers are a type of hyperdimensional system. And then they formalize how that works. So I think it has the tools to do it. The question is it being prompted by the training set to do that? Because to me, that this isn't how even humans learn. Like you sit down with a kid, you tell them, like, here's the basic, how to add numbers 1 to 10, how to carry the digit and all that. But then the more harder stuff is very formulaic. You show like the process, and none of these seem to show the process. They just seem to show like the input and result for the most part, as far as I can tell. So I think it's just the data is probably not very good for the task.
Well, that's where the chain of thought prompting comes in. And these models have done. They've been able to explain jokes.
Yeah,
that has been some people's tests of are they intelligent?
Yeah, well, like the jokes and stuff is more of a I mean, there's regularities in comedy, like people repeat jokes, like for example, so it makes sense that in the sea of like information we'll find something like that, understanding that. But as far as like formal systems, as was explained, that's like, can I stochastically give you enough examples that you figure out the pattern? Like with a kid, if you give enough examples of 1 + 2 + 1, figure out how addition works, or do you still have to explain to them the formal system and then they practice it and apply it? Like it seems to be very two different.
Yeah.
Right.
Yeah. It's like the first 50 years of AI was figuring out that these problems that we thought were signs of high intelligence in people, like the ability to play chess at a master level and doing calculus, that these things were easy to do with computers. And the basic, everyday things were actually hard. And now these new models have flipped it around again. And they can't go arithmetic. Yes.
Yeah. Question, but like talking about this primitive binding and composition operators, when you look like to the attention mechanism, it's at the first, when you look at it first, you're like, this is just the superposition, this is the binding or composition, right? This is the composition operation. But then there is sometimes a question, but is there a binding operation? But then kind of thinking in terms of matrix model as far as binary distributed representations, it has this CDT operation, which is
context dependency.
context dependent thinking. And there, the bind is actually done through the interaction of the things that are already in the superposition. And in a way, there is a softmax in the attention activation. And it also kind of, then of course, the result of the softmax depends on what things you're combining together. So in a way, it could be that like when doing the softmax, it's kind of very, very implicit way of doing some kind of binding. And then it's like, you know, kind of very implicit binding and composition all together. I have no idea how to probe it, like how to demonstrate it, but that might well be a reason that the attention mechanism actually has both in a style that is very, very similar to Dmitri's ideas of as VDR model.
I think the vehicle design is also the masking. So that the masking is the vehicle, and then what you're saying is how it actually achieves that process. But if you didn't have a mask language model, would it still work? I don't think so.
But yeah, then of course there is still a question, right? It's almost like the nature versus nurture, right? Like, I mean, these models are there, but they require credible amount of data. But there are some very important principles that can be formalized in somewhat different way. For example, in order to make your model like have sort of more inductive bias in your model, so that instead of using billions and millions of token, do it, I don't know, with unreadable like small amount of text.
This
It's very small compact corpora, just because you have already a lot of inductive bias in the model.
There's two very unsatisfying things about these large language models. One is they basically are absorbing the entire written output of humanity, which very soon will consist mostly of output from other language models. And so that's one thing. And the other thing is it's incredibly difficult to understand what they're doing. So that comes back to the transparency question.
It seems like they're trying to mimic what humans would do. Like, what would a human do in the situation? And they try to mimic, even if it doesn't make sense, it sounds convincing enough. To fool even the human, but when you look at it, it doesn't make sense actually. And that probably has to be because it's not embodied. Like a lot of the words, they don't have any meaning. Like I saw a cat was seeing me to, you know.
It doesn't have any grounding to the external world, like Ross was talking about. Its only grounding is to other text.
So is this when you say this is the limit of what you can do with language?
I have no idea.
I mean, I think it would happen. I mean, essentially, if all it's got is text, it's a formal system. So it's not. It has no reference to anything else. And so, you know, the way I'm interpreting it is because the text it's trained on has been produced by humans and sort of reflects regularities in the human world, necessarily to some extent it conveys information about those regularities, but it only conveys information about those regularities, not about the world which generated those regularities. I mean, there was Tony and I were chatting last night. There was earlier this year at the Santa Fe Institute, there was a workshop organised by Melanie Mitchell called, I think, sort of the barrier of meaning, something like that. And so it was a whole series of talks, and they're all video recorded. They're on YouTube. Basically, what is meaning? Do things like this have it, and so on. But I mean, to me, it's. I mean, if you've got a formal system, basically it can shuffle stuff around according to its rules, but that's the only constraint there is. So if you've got a formal system, which is where those components of the formal system can be put in some relationship to an external world, then any formal system which is generative enough, productive enough to generate all the states that correspond to real things that happen in the world will certainly be able to generate a whole vastly larger amount of things which correspond to rubbish states in the world. So if you've got, if you say we've got a brain, it's effectively there's a formal system because you've got the hypervectors or whatever being shuffled around according to its own internal logic. what it needs to do is to learn the constraints such that even though, those that states which are syntactically possible, but statistically unlikely in the outside world, no longer occur in its internal dynamics. So it's this notion of self-updating grammar so that you're adding distinctions to your grammar that allow it to better and better model the external reality. But these things have no direct contact with that external reality, so they're just picking up a set of regularities, but it's not sort of the generative set of regularities.
One very funny example that I saw was somebody that was like, Paul was alive at 2 p.m. And he was alive at 4 p.m. Is he alive at 3 p.m. then? The LLM basically said, I don't know.
Yeah, I mean,
because it doesn't know.
Yeah, I mean, so one take on compositionality is, it's really more a reflection of the external world. We live in a world in which the concept of objects actually has predictive value, that there are things which are internally predictive of themselves, which sort of tend to move around discretely and so on, and which can be stacked up on top of each other and joined together to do bits and pieces, and that things like actions can be stacked together in a sort of functional compositional sense. So if we live in a world where the processes can be reasonably compactly described in terms of compositional stuff, and you want to model that with some formal system, then you'd want compositionality in the formal system. If all it was just general tendencies in the outside world you're measuring, then a regression model will do quite nicely, thank you. So, yeah.
Yeah, and so to just say one more thing about in response to your question, language is pretty rich. It's a lot. If all of these models their only input is language, we can still go a long way with that. After all, literature, people construct entire worlds and communicate them with language, and it's rich. People interact through language. It's a pretty rich domain.
One of the supporting premises is language supporting of human intelligence. Yeah, so one of the supporting premises. There is opposing views, but supporting.
I think one of the issues in sort of early AI-ish kinds of stuff is that people tend to think of, there's this language of thought hypothesis that somehow or other there's something that looks like a language in the brain, which is the stuff in which mental processes happen. And that's probably quite reasonable, but you don't want to equate that to language in the external linguistic sense, so that each individual person, I think, has some compositional modeling thingy going on in their head, which is all about relationships to the outside world. And yes, you can make a set of actions, which is flapping your mouth around and moving air in and out, which convey something about that. But it's like gestures. I mean, think about, to me, language is not determinative. It's up to the person who's receiving what you've just said to then try to reconstruct a world model in their internal mechanism, which is consistent with what they already know and what you said. But the words you actually say don't actually directly get translated in. It's actually work on the part of the receiving system to then say, what was suggested by that.
Language is the ultimate compressed communication. Essentially, you're assuming the target has the same hardware as you, roughly same experiences, same eyes, same ears. So when you say things like I saw a cat, the person knows what you mean by that because they've seen a cat too, right? So, but if they haven't seen a cat, then all they know is the patterns of what you're saying.
But I think the point is, to me, is that those words that are being said, there's not a one-to-one relationship between them and what gets constructed in the brain of the listener. So we might have just 1 minute previously said, when I say I saw a cat, what I really mean is it's time to go for coffee. And and you would then create the appropriate representation from that when you next heard those words. So it's the words themselves are completely arbitrary. That there's conventions about how what result may occur, but it's idiosyncratic and it's evolving and all the rest of it. Whereas a lot of the stuff about, I've got these answers out of Chat GPT, and does it indicate that it's compositional or intelligent or whatever? I think the confusion in many people's minds is that there's actually meaning inherent in the words. The words are just a prompt for the listener to construct a meaning. The meaning's not actually in the words themselves.
I think it really gets back to like this, the model again is not learning from any external reality. Like it just has it doesn't have meaningful representations of these concepts. Like all of its internal representations are again just purely what it can pick up from text. And it'd be interesting to look at. There's a lot of interest in scientific computing for can we somehow combine training on these scientific problems with the actual physical equations so that you can eliminate, again, these seemingly like reasonable solutions, giving the training data and the internal tokens with the physical laws constraining what is and is not a valid solution. So in a way, it would be interesting to say, like, how could we combine some of these large language models with some of the, again, like constraints of physical reality? Like, it can't learn statistics the way that we do by interacting with the world, but maybe there's some kind of other training data that could be provided to kind of do this thinning of internal representations.
In vision, they do that quite a lot. They have those like, what do they call it? My advisor worked on that a lot. Basically, like, if you do good old fashioned vision instead of like learning stuff where it's like homographies and things like that, there's some assumptions you can make. Like, for example, the object is closer than further, then something is further away. And in the equation, suddenly things become much easier to actually formalize, right? And so something like a language, that's a weird suggestion.
So I think we're going way over time, but Chris has been, I think Chris has a comment, he's been waiting patiently.
Yeah, so not to keep two people for break too long, but just one maybe quick thought and then a question of like, where VSA could kind of fit in. So one is like going back to the photo and Polition debate. I find it interesting how much focus there is in compositionality when I think photo and Polition are framing it in terms of systematicity, and then compositionality is a sufficient condition to achieve systematicity. But I think an interesting point here is that like maybe what these language models are showing is that like compositionality is not, if they are not compositional, is not necessary to achieve something that, at least as far as we can tell, is exhibiting kind of systematic behavior. Where by systematic behavior, I mean something like what we in machine learning would call like conversation, which is that if you can think about some things or do addition of some numbers, you can also do addition of other numbers. If you said 2 + 2, or you can do 2 + 2 and you said 4, but then you had some other numbers and then you said that was 4 too, we'd question not your ability on that particular problem, but your ability to do math in general. I took that to be the kind of point there. But maybe there still is a point about VSAs and other kinds of models, which is to say, what large language models are doing is they're solving these kinds of problems and they're exhibiting systematicity without compositionality. And yet still it could be true that a compositional kind of approach, or one that is explicitly compositional, and maybe this is compatible with like these chain of thought reasoning approaches, is one that like shows its steps in terms of like compactness, in terms of transparency, in terms of being able to be run in a kind of scalable way. And maybe the way that these LLMs get there is a very different kind of route. But that doesn't mean that, okay, from like either cognitive science, like what are the kind of internal representations point of view, or from like a computer science kind of data structures, what are good efficient algorithms we can run point of view. It still seems like there's a lot of exciting work to be done.
Yeah, I totally agree. I think that's an important distinction. I totally passed over the one between compositionality, which is more like the mechanism, and systematicity, which is the behavior.
So some papers show some non-significant percentage of people don't have an internal monologue, right? So like something like 8% of people, they don't have an internal monologue. So
that's scary.
What does the compositionality look like then? It can't be formalized as like a syntax. What are they doing?
I think that gets to the question of like, is the inner thought process like explicitly linguistic in terms of being like language? And I would suspect that those people would still have a model of the world that can represent part whole structures, even if they can't.
It's fascinating.
Are you talking about like, just thinking in anything other than language? Because like I know like some people think in images, like I mostly think in images instead of actual words.
Yeah.
And so it's still like, it's not that, people like me don't have internal like streams of thought. It's just that maybe it's not like necessarily in words, like.
All right, it's not words, that's specifically what we're saying that the monologue is not in words. So you're not thinking like, I'm gonna go over there and I'm gonna grab this cup. Instead, it's just like, I'm gonna, and you don't think about what this is or what. And that could be because you're a visual learner. So you visualize the gravity and that's verbalize it to yourself.
Yeah. Talking about caps, the caps are over there. Just we wrap up this keynote. Thank you, Tony.